So now we're going to move on to finding volumes and areas as well using polar coordinates. In this section, we're going to look at double integrals in polar coordinates. Now just recall from your previous pre-calculus class the relationship between our rectangular or Cartesian coordinates and our polar coordinates. So recall that an x value is equal to r cosine theta, a y value is equal to r sine theta, r squared is equal to x squared plus y squared, and then tangent of theta is equal to y over x. Oftentimes it's easier to calculate a volume or even an area by using polar coordinates as opposed to Cartesian or x and y coordinates, and this is particularly true of anything that is curved or maybe circular in nature. What's happening when we look at polar coordinates? So if you look at this diagram here, let's say our region, and then this diagram is our region, similar to a region in the xy plane. Let's just suppose that we want to compute this a volume, and we have this following region that's shaded. So this region is going to, now this is just a plane region, it's going to correspond to a surface Z and will create a volume. So this region in an XY plane would be made up of little areas of rectangles. So in polar coordinates, we're also going to have an area. And look at this red region here. We're going to have an area, and it's called a polar rectangle. Not quite a rectangle because it's curved. But notice that if we look at the sides here, we're going to have some distance here, and if you notice it, our theta value. So we're going to have some distance theta, right? And we're going to have some distance r. So we have a delta theta and a delta r. And what those two values will give us is our delta A for our area. So each polar rectangle is going to correspond to some values, some z values, and it'll create a volume. So if we just add up all those volumes, it'll give us the volume for our whole region. Now if we just take the limit as the delta A's get closer and closer to 0, that would give us our integral below. Okay. So something we have to remember that when we're in polar, we're going from some smaller theta value to a larger theta value. It's always small to large. And for our purposes, we're going to use r values that are positive, or 0. Recall that when you are working with polar coordinates, it is possible to have a negative r value, but we'll just be dealing with positive r values. To compute the double integral over a polar rectangle, you're going to have some region R. It's going to have an R and a theta value. And here notice that our R values are going to be between some A and B value, some numbers, but we're only looking at R values that are greater than or equal to 0. Theta is going to go from some alpha to some beta value, where beta minus alpha is less than 2 pi. So our double integral over our polar region for our z function, which is a function of r and theta, so remember this is just z values, is going to split up into, here we have r from a to some value b, and we have theta values from alpha to beta. This region dA is going to break up into r times dr d theta. That r has to be there. In later sections, we're going to actually prove why this is true. But for now, whenever you're trying to compute a double integral in polar coordinates, you have to have that r dr d theta. Well, let's go ahead and use this to find the volume of a solid bounded by the paraboloid z equal to 4 minus x squared minus y squared and the xy plane. Okay, so first of all, we're going to sketch this. Again, I'm apologizing ahead of time for my sketch. So we have some z function, some z-axis, x and y, the usual. So the paraboloid is z equal to 4 minus x squared minus y squared. So when x and y are 0, z is actually at 4. I think I'm going to do this in blue. Here, this is going to be bounded between this paraboloid and the xy plane. So it's going to stop at the xy plane. And then if x and z are 0, then y is going to be 2. And same for the x value. So we have this paraboloid coming down. And it's, sad drawing, bounded by the xy plane. So remember, the region that we're looking for is the region in the xy plane. That's going to determine our limits of integration. And then for every point in the xy plane, it's going to correspond to some z value, which creates our volume. If I was just looking at this region in the xy plane, what I have is I have this circle. Oops. Well, that's a sad circle. So I have this circle. Oops. I'm going to erase this whole circle because it's irritating me. Do it again. All right, so I have a circle, 2 to negative 2. So if I was to determine my limits of integration and not write this in polar, keep this in xy. Remember, the upper part, I'll do this in green, would be the equation y equal to the square root of, and that's going to be 4 minus x squared. Maybe we'll use blue for the lower piece. That would be y equal to negative square root of 4 minus x squared. And I don't want to do that. I want to use polar. The reason why I want to use polar coordinates instead is that if we look at this circle, in terms of polar coordinates, we can look at starting at a theta value of 0, traveling around this circle, and ending off with a theta value of 2 pi. So that has us going completely around the region. So again, remember, this is our region R that gives us our limits of integration. So theta is going to go from 0 to 2 pi. What are our R values? So remember what our R value is. That's a distance out from this, from here, from the origin. So I'm going to do this in green. So our R values are going to be this distance here that starts at a 0 and ends at 2. So pick any point as we go along, and it goes, the R value goes from 0 to 2, 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 and so on. So it's important to remember the movement here. Now I'm going to set up my volume. It's going to be equal to, I'll put theta first, or on the outside. Theta values from 0 to 2 pi. My radius is going to go from 0 to 2. My integrand is z equal to 4 minus x squared minus y squared. And then this is polar, so it's r dr d theta. Now since r and theta are constant limits of integration, I can exchange the dr and the d theta, but I'm not going to. Something to note when you're working in polar coordinates and you're doing these double integrals is that your theta value will always be constant. So you can always leave it as the last thing you do. R in this case is constant, but we'll see in later examples that R may be written as a function of theta. So I do have a problem with this volume, and the problem is here. The integrand is in terms of x and y, but I'm integrating with respect to r and theta. So I need to change this so that it's in r's and thetas, there's no x and y. So off to the side here, 4 minus x squared minus y squared is the same as 4 minus in parentheses x squared plus y squared. And I know that x squared plus y squared is r squared. So I can simply write this as the integral from 0 to 2 pi, integral from 0 to 2, parentheses 4 minus r squared, r dr d theta. And the first thing I'm going to do is get rid of the parentheses, distribute the r, and then I'm going to integrate with respect to r. It's 4r minus r cubed dr d theta. And the 4r becomes 4r squared over 2, or 2r squared. So this is the integral from 0 to 2 pi. 2r squared minus r to the 4 over 4, integrating from 0 to 2 d theta. And then putting in 2, I have 2 times 2 squared, so that becomes 8 minus 2 to the 4 over 4 is 4, which gives us a 4 total. Putting in 0 is just 0, so this becomes the integral of 4 d theta after you evaluate. And that would be 4 theta evaluated from 0 to 2 pi. And my volume is 8 pi. So again, your theta values will always be constant, so you can always do those last. The r values, in this case, they were constant, but sometimes not. Sometimes they'll be written as a function of theta. You always have to be careful that you're going from a small theta to a large theta. And you have to be careful on choosing the correct r values. Okay, so what I want to do now is go back to example 6 from the previous lecture, 15.2. I don't know if you recall this example, but originally we had completed this problem in 2 pages, and I even skipped some of the algebra steps so it could fit in the 2 pages. But now instead of using x and y, we're going to try this same problem from 15.2 using polar coordinates. Recall our region between the 2 paraboloids. Again, you get to see my beautiful graphs. We had the paraboloid z is equal to x squared plus y squared. This would be a parabola opening upward. And then we had another parabola z equal to negative x squared minus y squared plus 18, which is a parabola opening downward. So we're looking at the intersection of these 2 regions. It created this volume in between the 2. Now when we were trying to figure out our limits of integration, what we did was we took that intersection of those 2 regions and we looked at its shadow in the xy plane. So that became the region in the xy plane of the circle x squared plus y squared equal to 9. So how did we get that circle? Well, to get that, we simply set these two z values equal to each other and solve. So we set x squared plus y squared equal to negative x squared minus y squared plus 18. Solving, we got x squared plus y squared is equal to 9. Okay, so this region, instead of writing it in terms of rectangular coordinates x and y, I think I would rather write it in terms of r and theta. So again, if I was to complete this region, my theta values would start at 0. I would go all the way around this circle, come back to a theta value of 2 pi. So theta can go from 0 to 2 pi. My r values, recall that I'm going from the center to the outside, and I'm creating my region, filling in this region from r values that go from 0 to 3, 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 0 to 3. So r goes from 0 to 3. I have my limits of integration. All I have to do is figure out what my integrand is. So my integrand is the upper minus the lower, as it was when we were working with x and y coordinates. In this particular diagram, the upper is this diagram in green, which is the negative x squared minus y squared plus 18. So if z is equal to negative x squared minus y squared plus 18, the negative x squared minus y squared is going to be negative r squared plus 18. And then the lower function is rz squared, maybe I'll move this up a little bit, is x squared plus y squared, so that's z is equal to r squared. So again, I have to switch everything to polar, including the integrand. Putting all of this together, I can look at my theta values going from 0 to 2 pi, but let's mix this up a little bit. Notice that my z functions, the volume they create is symmetric about the z-axis, meaning you can rotate it around the z-axis and it remains unchanged. What that actually means is that if I'm looking at, say, quadrant 1, the volume that corresponds to quadrant 1 is going to be the same as the volume for quadrant 2, for quadrant 3, and for quadrant 4. So instead of integrating from 0 to 2 pi, I could choose to integrate from, say, 0 to pi and then multiply by 2. Or, I think I'm going to do this, I'm going to integrate from 0 to pi over 2. And change my limits of integration from 2 pi to pi over 2. And then I'm going to multiply that volume by 4. So this is something you can always do if your volumes are symmetric. So my volume, instead of going from 0 to 2 pi, I'm going to do 4 times theta from 0 to pi over 2. Don't have to do it. Can always just go from 0 to 2 pi. My r values from 0 to 3. My integrand is going to be the upper, which is the negative r squared plus 18 minus the lower, which is r squared, so minus r squared. And then it's r d theta. I'm going to go ahead and combine, so that's 18 minus 2r squared, and distribute the r in one step. To get the integral from 0 to 3, this becomes 18r minus 2r to the third dr d theta. So for integral from 0 to pi over 2, 18 r squared over 2 becomes 9r squared minus 2r to the 4th over 4 becomes r to the 4 over 2, and evaluating from 0 to 3 d theta. So when we evaluate that integrand and put in 3, it becomes 81 minus 81 over 2, which is simply 81 over 2, and then minus 0. So it's just 81 over 2. Integrating with respect to theta, this becomes 4 times 81 over 2 times theta, evaluated from 0 to pi over 2. So that simply becomes 81 pi over 4 minus 0, and you can see that the 4's will cancel. Now recall from our previous section that when we completed this integral, we got 81 pi, which is what we have when we switch to polar. So same answer, but notice that I could easily fit these computations into one page. In this next example, we're going to look at what we call annular regions, which are simply rings. All that means is that your R value, instead of going from 0 to some number, the R values are going to not start at 0. In this case, we're going to find a volume bounded by this surface z equal to xy plus 6. So recall that that z function, that's going to be our integrand. And it's going to be over this annual region R, and R is equal to the points R theta, where the R values go from 1 to 3, and the theta values go from 0 to 2 pi. So what's nice is when you do get an annular region, you are given R. Those are your limits of integration. You don't have to find them. I'm going to go ahead and graph this region anyway, so you could see where these R values came from. Well, the theta values are going from 0 to 2 pi, so it's a complete circle. The inner ring is an R value of 1, so that would just be a circle of radius 1. The outer R value is 3, so that would be a circle of radius 3 for my sad circles. Which means the region that we're integrating with respect to is just going to be this shaded region between these two circles. Okay, so that's what we call an annular region. I already have my limits of integration. I can just set up my volume, except for my z function is written in terms of x and y. So the first step is to write my z functions in terms of r and theta, because that's how my limits of integrations are written. Recall that x is r cosine theta and y is r sine theta. And then I have a plus 6. If I multiply those two r's, I get r squared is equal to cosine of theta sine theta. Now I can see that eventually I'm going to have to integrate with respect to theta, and I'm going to have to integrate cosine times sine, which is a product of functions. So I either have to use a trig identity or I have to use a substitution to evaluate. So before I go any further, I'm just going to go ahead and switch the cosine sine into sine of 2 theta. So recall from your trig that sine of 2 theta is equal to 2 sine cosine. So if I simply divide both sides of this equation by 2, on the right the 2's cancel, and I have that sine cosine is equal to sine of 2 theta over 2. So I'm going to replace this cosine sine with sine of 2 theta over 2, and then plus 6. And in fact, that over 2, I'm just going to pull that out and write that as 1/2 r squared sine of 2 theta when I write out my volume formula. In our previous example, I used symmetry to go from theta values 0 to pi over 2. Notice that I cannot do it in this example, and it's not because of my region. That is symmetrical. It's because of my integrand. There is no symmetry here. Is that how you write symmetry? So since there's no symmetry with z, that z surface does not revolve around the z-axis, then I cannot just go from, say, 0 to pi over 2 or 0 to pi. I have to use theta values from 0 to 2 pi. My volume is then equal to the integral from 0 to 2 pi, the integral from 1 to 3. This becomes 1/2 r squared sine of 2 theta plus 6 in parentheses r dr d theta. Getting rid of the parentheses and distributing the r, I have 1/2 r to the third sine of 2 theta plus 6r, and then dr d theta. Integrating with respect to r for the inner integral, I remember the sine of 2 theta just is constant, so it becomes r to the 4 over 8 times sine of 2 theta plus 6r squared over 2, so that becomes 3r squared. Evaluated r values from 1 to 3, d theta. So my integral from 2 pi, inside if I put in 3 for r, 3 to the 4th over 8 becomes 81 over 8 sine of 2 theta plus 3 times 3 squared, 27, minus 1/8 sine of 2 theta plus 3 d theta. Combining like terms, I have 80 over 8 or 10 sine of 2 theta plus 27 minus 3 or plus 24 d theta. Antiderivative of sine of 2 theta is negative cosine 2 theta over 2, so this becomes negative 5 cosine of 2 theta plus 24 theta, evaluated from 0 to 2 pi. And then plugging in 2 pi for theta, I have negative 5 plus 48 pi, and then minus, putting in 0 for theta, minus negative 5. So the negative 5s will cancel out, end up with 48 pi. Now let's move on to r values that are not constant. So here we're looking at general regions, which means that our theta values will be constant, but our r values may be a function of theta. Looking at this diagram, you can see that if you're looking at the distance r between these two curves, it's not going to be the same. The distance changes as we go around because the two curves are not the same distance apart from each other, which means our r values are not constant. In this case, our r values are going to be some function of theta. But here, just remember that we are making sure that our r values are not negative, that they're always greater than or equal to 0. Also notice that the theta values are still constant. So in that case, we want to make sure that we always evaluate our r's first and our thetas last, because they would be the constant limits of integration. In our next example, what we're going to do is we're not going to evaluate the integral, we're just going to set them up. In example 4, we're going to write an iterated or a double integral for the following regions in the xy plane. So it says the region, for part A, the region outside of the circle centered at 0, 0 with a radius of 3, and inside the circle r equal to 6 sine theta. So although the regions are in the xy plane, notice that one of my circles is r equal to 6 sine theta. It's in polar form. So I'm going to write everything in polar form, which means that this circle centered at 0, 0 with a radius 3 in polar form, that would be r equal to 3. So part A, we want to look at the region outside of this circle, r equal to 3, and inside the circle, r equal to 6 sine theta. Let's go ahead and sketch this region. Okay, so r is equal to 3, and r is equal to 6 sine theta. That's a circle as well. On the y-axis again. Excuse my drawing. So this region is going to be outside of the blue circle and inside of the green. I'm going to shade this. Maybe I'll use red. So this is the region that we're talking about here. So first of all, we have to determine our theta values. We're going to look at where these two circles intersect. So I could simply set them equal together. Equal to each other, sorry. So I'm setting 6 sine of theta equal to r is equal to 3. Or in other words, sine of theta equal to 3 divided by 6, so 1/2. Notice that sine is equal to 1/2 when theta is equal to pi over 6. So that would be this first theta value. Oops. So that would be pi over 6. And then the next time sine is equal to 1/2 would be at 5 pi over 6. That would correspond to this second value. So I have my theta values. I just have to figure out my r values. So remember that I'm looking at the distance between these two. So the smallest r value, if I pick any point here, the smallest r value is 3, and then it goes up to 6 sine theta, right? Because this is 6 sine theta. And this is r is equal to 3. So pick any distance here, and it's going to go from 3 to 6 sine theta, 3 to 6 sine theta. Which means my theta values are going to go from pi over 6 to 5 pi over 6, and my r values are going to go from 3 to 6 sine theta. So it's a little bit of a challenge here trying to figure out your limits of integration. Now I wasn't given an integrand, so I will just use a general function z equal to some function of r and theta. When I set up my integrand, it's going to be the double integral where theta is going to go from pi over 6 to 5 pi over 6, and r is going to go from 3 to 6 sine theta. My integrand is just some z function with respect to r theta, and it's polar, so it's r dr d theta. Again, we're not evaluating, we're just setting it up. I want to make sure everybody understands what the language is here. Let's go ahead and look at part B. Oops, I want to use black. So in part B, it has the same circles, right? Circle centered at 0, 0 with radius of 3, and the circle 6 sine theta. But this time it's not saying outside, inside, it's saying bounded by. I'm going to go ahead and draw this again. So we can see the circle with radius of 3, and the other circle is 6 sine theta. Maybe I'll shade this in yellow. So when we look at bounded by, it means between. Okay, so these two intersect at those same theta values, right? This was pi over 6, and then the other theta value was 5 pi over 6. The problem is and it's kind of hard the way that I drew this because I am hand sketching this, is it doesn't quite get all of that shaded region. There's a little piece below theta values of pi over 6 and 5 pi over 6 that's not accounted for. So if I'm just looking at theta values from pi over 6 to 5 pi over 6, that would just be this yellow upper shaded region. I'm actually going to label all these different regions. I'm going to call this upper region, or the region between pi over 6 and 5 pi over 6. I'm going to call that R3. I'm going to let R1, and here maybe I'll use red again, and R2 be these smaller regions. They're actually going to have the same area. Oops, R2, sorry. So from theta is equal to pi over 6 to 5 pi over 6, that R3, that's going to be described a little bit different from R1 and R2. So let's look at R1. These are the points R theta, such that, let's think about our R values. Sometimes it's easiest if we draw a little line. First of all, notice that we're starting at theta is equal to 0, and then we're going to theta is equal to pi over 6. And if I draw a little line anywhere in here, it's going to start with an R value of 0 to an R value that corresponds to that green circle, and that green circle is 6 sine theta. So the R values are going to go from 0 to 6 sine theta. And the theta values are going to go from 0 to pi over 6. I'm going to go to R2. It's described almost in the same way. You just got to be careful with your theta values. So notice that if I look at any R value, again, remember we're starting from the inside and we're going out, it's going to go from 0 to the green curve, which is 6 sine theta. So same R values as in region 1. It's just the theta values are going to change. Notice that my theta values are going to go from 5 pi over 6 to a theta value of pi. Oops, do it in black. Oops, can't write. I gotta erase that, it's gonna irritate me. Okay. And finally, the region 3. These are going to be points R theta. Think about our R value in this case. If I look at an R value, it's going to go from the center to the blue curve. So it's going to have R value from 0 to 3, 0 to 3, 0 to 3. Doesn't matter where I go. From theta pi over 6 to theta 5 pi over 6, the R value that corresponds to that region would be 0 to 3. Okay, and that would be our theta values from pi over 6 to 5 pi over 6. So you see how tricky this can be. So now if I set up my integral, since I have 3 separate regions, I have to set up 3 separate integrals. Okay? I'm going to have the integral from 0 to pi over 6, 0 to 6 sine of pi, my function with respect to r theta, r dr d theta. So that would be region 1. I'm going to have to add this to the integral from Maybe I'll go pi over 6. Oops. Can't write. Pi over 6 to 5 pi over 6. In this case, the radius goes from 0 to 3 of my function r dr d theta plus, I'm going to go down here, plus the integral from 5 pi over 6 to pi, radius goes from 0 to 6 sine theta, my function r dr d theta. So look at, with just a change from outside inside to bounded by, that really complicated the description and our limits of integration. So just be careful about the region that's being described to you. But now let's just review some common polar curves that you may have seen in your pre-calculus classes. When we look at circles and spirals, if r is equal to some number a, that would be a circle. If r is equal to a times sine of theta, that's still a circle, but remember sine corresponds to y value, so that's a circle on the y-axis. If it's an r equal to a cosine theta, that's still a circle, but it corresponds to a circle on the x-axis because cosine corresponds to x values. Now if we have a spiral, if r is equal to some number times theta, that would be a spiral. Now in the case where a is positive, that's a spiral going, our usual direction is counterclockwise with polar curves. If a is negative, that's going to change the direction of our spiral. Limacons are sometimes called cardioids if they have a special a and b value which are equal. Anyway, they take the form of r equal to a plus or minus b sine theta, or r equal to a plus or minus b cosine theta. Now in these particular examples, did you see these 4 examples? That would be if it was a sine, because notice these are graphed on the y-axis, which is sine. If it was flipped over onto the x-axis, that would be cosine. If the a value is smaller than the b value, you're going to have this inner loop here. If a and b are equal, that's what we call our cardioid. It looks like a heart, so cardiac. A greater than b, notice that it starts getting more rounded. And if a is greater than or equal to twice b, then it becomes more like a circle. Okay? So as a gets larger, b gets smaller, it becomes more circular. Another common shape is what's called a rose. So that could be r equal to a sine n theta, r equal to a cosine n theta, and the number of what we call leaves, I don't know why they call them leaves. If it's called a rose, it should be called a petal. Anyway, in your book they call them leaves. So the number of leaves is determined by the n value. If n is odd, then there's n leaves. If n is even, then there's twice that, or 2n leaves. So for example, if we had r equal to a cosine of 2 theta, since n is 2 and 2 is even, then we double that and we have 4 leaves. If r is equal to a cosine 3 theta, 3 is odd, so it's 3 leaves. And if we have r a cosine 4 theta, 4 is even, so we double it, we have 8 leaves, and so on. The last common shape is what we call a lemniscate. That would be an infinity or a figure 8 shaped. This is actually given as an r squared. So if r squared is equal to a squared sine of 2 theta, then it's going to be that infinity symbol that's sort of slanted on the diagonal. But if it's an r squared equal to a squared cosine of 2 theta, then it's the infinity symbol figure 8 or lemniscate that's on the x-axis. So these are some common shapes that you may come across, or some vocabulary that you may see in your homework. Now remember, we were figuring out volumes, but we can also go back to figuring out areas using our iterated or double integrals. Now remember, when we're figuring out an area as opposed to a volume, all we have to do is have an integrand of 1. Okay? So just be careful what you're being asked to find. In example 5, it says compute the area outside the circle r equal to the square root of 3, inside the lemniscate r squared equal to 6 cosine of 2 theta. So first of all, I'm finding an area, which tells me my integrand, or my z function, is simply equal to 1. Now let's look at our region. I'm going to sketch this, and again, it's not really going to be to scale. I have r equal to the square root of 3, so that's just a circle centered at the origin with a radius of square root of 3. And then I have cosine 2 theta with the r squared, and there's a 6. So that's going to be my figure 8. Oh god, this is sad. And it's cosine, so it's on the x-axis. My integrand is just 1. I'm finding an area. I have to determine my limits of integration. I have to look at where these two intersect. And then remember, this is going to be the area outside of the circle, but inside the lemniscate. Let me go ahead and zoom this in a little bit. So I'm going to shade the region that I'm looking at. And that comes in 2 pieces, outside circle, inside lemniscate. Now I can use symmetry. Remember, my z function is just 1. The integrand is 1. So I'm just looking at these areas. And I can see that these 2 areas are going to be the same. So maybe I can just compute this first piece and then times it by 2. That's one option. But even though you can't tell by my drawing, the quadrant 1 and quadrant 4 actually are going to be the same. So maybe instead of going from these 2 theta values, by the way, what are these theta values here? Oops, I don't want that. So if I look at these theta values, what theta values do they correspond to? Well, if you set them equal to each other, unfortunately this is an r squared. Right? So the lemniscate is an r squared, but remember, r is equal to the square root of 3. So all I have to do is simply plug in the square root of 3 for r in the other equation to get the square root of 3 squared equal to 6 cosine of 2 theta. So that would be 3 over 6 is equal to cosine of 2 theta, or cosine of 2 theta is equal to 1/2. So when is cosine of 2 theta equal to 1/2? Well, cosine is equal to 1/2 at pi over 3. But this is a 2 theta. So that means 2 theta has to be equal to pi over 3 plus 2k pi. Or in other words, theta is equal to pi over 6. So this would be theta equal to pi over 6. So just reviewing your trig. Now that would mean that this theta value here, which is actually 11 pi over 6, but remember, we have to go from small to large. So that's actually negative pi over 6. But I don't want to have a negative limit of integration because I just don't want to deal with it. So instead, what I'm going to do is I'm going to look at theta starting at 0, and I'm going to look at this first piece here, figure out what that area is, and just multiply it by 4. So I'm going to look at my theta values going from 0 to pi over 6. But what are my r values? Okay, let's go back to our diagram. If I pick any r value in this region, I'm going to start here at an r value of square root of 3, and I'm going to end up on the outside of this curve. But the outside of the curve is r squared equal to 6 cosine of 2 theta. I need r, right? So this is r squared equal to 6 cosine of 2 theta. So let's go ahead and figure out what r would be. I can clearly see that it's going to start at square root of 3, right? This is r is equal to square root of 3. So if r squared is equal to 6 cosine of 2 theta, that must mean that r is equal to plus or minus, but remember we're choosing the positive r. So that would be the square root of 6 cosine of 2 theta. So my smallest r value is the square root of 3. And then the largest is going to be the square root of 6 cosine of 2 theta. So you do have to be careful when you're dealing with the lemniscates that have an r squared in the equation. All right, let's put all this together. We have our limits of integration. I'm just going to do the first piece and I'm going to times it by 4 so that my volume is going to be, or my area, sorry, my area is going to be equal to 4 times, I'm going to do theta values from 0 to pi over 6. And my r values are going to go from square root of 3 to the square root of 6 cosine of 2 theta. Remember, my integrand is just 1, but I'm in polar, so I still have an r dr d theta. That would be 4 times the integral from 0 to pi over 6. The r becomes r squared over 2. I'm going to be evaluating this from the square root of 3 to the square root of 6 cosine of 2 theta, and then d theta. Now I know that when I put in these square roots, since this is an r squared, they're going to cancel. But also notice that the over 2, I'm going to pull out this 1/2. I don't feel like dealing with that. So that I have 4 times 1/2 or 2 on the outside. And the integral goes from 0 to pi over 6. This is now r squared. And square root of 3 square root of 6 cosine of 2 theta, d theta. And that's just my personal preference. You could have left that in there. So when I plug in, the square roots are going to cancel. I'm just going to end up with 6 cosine of 2 theta minus 3. D theta. All right. Now, when I take the antiderivative there, cosine of 2 theta is going to be sine of 2 theta over 2. So the 6 over 2 turns into a 3. This becomes 3 sine of 2 theta. And this is going to be minus 3 theta. Okay, so plugging in pi over 6, 2 pi over 6 would be pi over 3. Sine of pi over 3 is square root 3 over 2. And in fact, you know what? I'm going to take these 3's out and I'm going to put it in the front here. So that's going to be 6. Sine of pi over 3 is square root 3 over 2. Minus pi over 6. And then putting in 0, sine and 0, 0. and then theta at 0 is 0. I could just leave it like that, or I could distribute the 6, because I can see things would cancel, to get 3 square root of 3 minus pi. Okay, so that's finding the area. So the last thing we're going to talk about in this section is finding average values. But we're going to do it in terms of polar coordinates instead of x and y. But this average value, this f bar, is the same. So before in rectangular coordinates, it was 1 over the area of the region times, and here I have a little typo, I forgot my dA in here, which in polar would be 1 divided by the area of the region, except for the integrand now has the r dr d theta. Instead of just simply finding the average value of the function, in example 6, I'm going to kind of mix it up a little bit. So let's say that we wanted to find the average distance between points within the upper half of a circle of radius a, centered at 0, 0, and the origin. So let's go ahead and draw ourselves a diagram to model this problem. So I'm looking at this half circle of radius a, and I'm trying to find the distance between any point within the upper half circle of radius a and the origin. So if you take any point in this half circle, I'm trying to find the distance from the origin to that point, any point. And we're going to add up all these distances and figure out what the average distance would be. So when you look at these distances from any point in the half circle to the origin, that's just a distance r. So my r values are going to go from 0 to, I could have a point on the half circle, which would be a. My theta values are going to start at 0 and going to go around to a theta value of pi, which gives me my limits of integration. Well, what is the area of this region? What is the area of this half circle? Well, the area of a circle is pi r squared. In this case, r is a, so the area of the circle is pi a squared, but I only need the half circle, so the area is going to be pi a squared over 2. So I have most of the pieces. The only thing I don't know is my integrand. What is my function that I'm looking at in terms of r theta? My function, I have to think about this, is adding up all these distances, adding up all these r values. So my function is simply r. That's my integrand. So it's a little bit tricky here. When I find the average value of my function, which is just these distances r, it's going to be 1 over the area, so I'm going to flip that and write 2 over pi a squared. Theta goes from 0 to pi. R is going to go from 0 to a. R is my integrand, r dr d theta. So 2 over pi a squared, integrand from 0 to pi. This r times r is r squared, which becomes r to the third over 3, evaluated from 0 to a. D theta, plugging in a. In fact, I'm going to pull out the 1/3 and write this as 2 over 3 pi a squared. So if I pull out this 1/3, then this integral is just going to be r to the third evaluated from a to 0, which is simply a to the third d theta. Now I'm integrating with respect to theta. A is just a constant, so that's going to be a to the third times theta. So I have 2 over 3 pi a squared, a to the third times theta, evaluated from 0 to pi, which then becomes a to the third pi. So I have 2a to the third pi over 3 pi a squared. And simplifying, canceling out the pi, this becomes 2a over 3. So that means for any radius a, the average distance between points from the origin to any point within that half circle is going to be 2a over 3. Okay, so fun problem to end up with. Anyway, that's it for this section.